ওকে, আশা করা যায় সমস্ত প্রত্যেকের কাছে এটা ভিজিবল হয়েছে, স্ক্রিনটা এবং সাউন্ডটাও আশা করা যায় সবাই শুনতে পাচ্ছ। কোনো রকম কিছু অসুবিধা হলে ইনফর্ম করবে। তো নেক্সট আমরা যদি কোঅর্ডিনেশন কেমিস্ট্রিটা জাস্ট প্রথমের দিকটা, এটা বেসিক কোঅর্ডিনেশন কেমিস্ট্রি ক্লাস 12 এর বইতেও আছে বা এইচএস এর যে সিলেবাসে আছে, যারা এইচএস পড়ায় তারা অনেকটাই জানে। তো সেই জায়গাগুলো আমরা জাস্ট ব্রিফলি একটু ডিসকাস করে বেরিয়ে যাব, ঠিক আছে? তো কোঅর্ডিনেশন কেমিস্ট্রি, তো ফার্স্ট হচ্ছে কোঅর্ডিনেশন কেমিস্ট্রি। হোয়াট ইজ কোঅর্ডিনেশন কেমিস্ট্রি? অর কেউ কেউ বলে থাকে কমপ্লেক্স কেমিস্ট্রি, রাইট? বাট আমি পরে আসছি। কোঅর্ডিনেশন কেমিস্ট্রি মিনস the part of the chemistry which discuss about the coordination bond. There is a coordination bond between metal and ligand, coordination bond between metal and ligand. So this is the main phenomena. Next, what is complex compound and what are coordination compounds? Coordination compound, what is the basic difference between these two? কারণ এটা একটা খুব কমন কোশ্চেন, বিভিন্ন ইন্টারভিউতে এটা জিজ্ঞেস করে। দে উইল আস্ক অলওয়েজ দ্যাট হোয়াট ইজ দ্য বেসিক ডিফারেন্স বিটুইন complex compound and coordination compound. So complex compound means any compound which form via the combination of any metal and any ligand, like beryllium acetate, zinc aromatic acetate, sodium acetate, sodium complexes. So all are like crown ether, all are crown ether type molecule, krypton type molecules, or are called complex compound. But coordination compound is that compound which only form coordination bond, and metal atom must have a coordination number. Metal must have coordination number, and metal ligand bond is totally coordination bond. But for complex compound, there are suppose sodium crown ether complex, or we can say beryllium acetate, very common, B4O-CH3C whole C. So these are the complex compound, but these are not coordination compound, because here no transition metal is there, here nature of bond is not coordination. Okay, so this is the basic difference between coordination compound and complex compound. So this is one of the most important part, because they in the interview time people ask. So now, before go into the inside into the chapter, we have to know about the coordination compound. And if we know about the coordination compound, then we first Werner's coordination theory. Werner's coordination theory. This is the first part. So Alfred Werner is the first inorganic chemist who awarded the Nobel Prize in 1913. This is very famous year, because on that year Rabindranath Tagore also won the Nobel Prize in literature. So Nobel Prize is awarded by different scientists in different field, but first inorganic chemist is the Alfred Werner who won the Nobel Prize, and year of 1913. In 1913, you know that three people get the Nobel Prize. One is Rabindranath Tagore, another one is in physics, Kamerlingh Onnes. If you know the electrochemistry part, that is conductance, so Kamerlingh Onnes is the second person, and in chemistry, Alfred Werner. That's why this 1913 is very famous for inorganic chemist people. So what is the basic theory of Werner's theory? Before going to the Werner's theory, we have some theory which was proposed by Jurgensson. First, we have to know about the Jurgensson's theory. Jurgensson's theory. Actually, Jurgensson's theory, suppose Werner's theories come like 1890 around, but Jurgensson's theory come like 1810 that time. And before that, which theories comes? There is no theory actually. Barthelot, one scientist, it is not a scientist, he is a dice maker, actually, dice maker. So this dice maker show the path for the discovery of coordination chemistry. Because actually what happened for the dice maker, সুইডেনে বিভিন্ন বাড়িতে রং টং করতো, তো রেগুলার রং করার সময় যে রঙের যে কন্টেনারগুলো ইউজ করতো সেই রঙগুলোকে কি করতো না কোথাওটা রেখে দিয়ে যেত, পরের দিন আবার এসে কালার করতো, বিভিন্ন কালারকে মিক্স করে করে রং করতো। তো একদিন কি হয়েছে, একটা স্টেবল মানে আস্থা বলে কি করেছে, ও ওই মানে কন্টেনারগুলো সব রেখে দিয়ে চলে গেছে। পরের দিন এসে দেখেছে হঠাৎ করে যে কালারটা রেখে গিয়েছিল কালারটা চেঞ্জ হয়ে গেছে, এবং হি ইজ টু মাচ কনফিউজড দ্যাট হোয়াট ক্যান আই ডু দ্যাট দ্য কালার ইজ নাও চেঞ্জেস। So then what he did, this is happening like 17th century, 17th century, Barthala. So then he brought all the container to the research lab in Swedish research lab and asked them what happened, please tell me. Then they found some new compounds within the container. This compound contain like ammonia and urea, and they discovered that this ammonia or urea comes from the urine of the sheep. That is the stable is for sheep. So sheep urine contain ammonia or urea, which makes different color with the chemical present in the container. So then they give some idea that something is happening here, and after that they also discovered that the color dye contains some cobalt, because on that time no chemical bond is discovered. So they isolate, there is cobalt is there is ammonia is there is chlorine is there. And then this theory is not established on the time. Then Jurgensson started his work with different cobalt complexes, Jurgensson's theory. And the cobalt complexes are like CO NH3 whole 6 Cl3, CO NH3 whole 5 Cl2 dot H2O, or CO NH3 whole 4 Cl2. So different compounds Jurgensson observed, and what he did, he measured the conductivity of the solution, and according to conductivity he showed that conductivity of the compounds, and according to his conductivity measurement he find out the number of ions in each complexes, and according to number of ions he gives some brief insight into the quantum chemistry. What actually Jurgensson did, Jurgensson told that there is a new bond is formed between the metal and ligand, because on that time there is no concept of the ligand, but Jurgensson's proposal was in such a way that he can give some information about a new type of compounds, okay, which can be later used as ligand. And according to Jurgensson, he measured the, what can I say, that he measured the conductance as well as their deep insight into the mechanism, that what actually he did. Suppose he told that CONH3 whole 6 Cl3, it contain, when he treated it silver nitrate, he observed that 3 AgCl is prepared, means precipitated out. That means there are 3 chloride ions are there, the conductance is due to 3 Cl minus 1. But when he treated like CONH3 whole 5 Cl2, and outer side maybe some water molecules are there, and treated AgNO3 or something like, Cl and Cl2 is outside, then he obtained 2 AgCl. Similarly, when he treated like CONH3 whole 4 Cl2 and another Cl is in outside, so he obtained 1 AgCl when treated with silver nitrate. But when he treated the CONH3 whole 3 Cl3, that composition complex, he did not get no AgCl. That means, so what would happen here? Because this compound have no conductivity, its conductivity is 0. And according to this concept, he tried to put forward some theory regarding that conductive measurement. And on that time, he proposed, so I just show some proposal structure of Jurgensson, that how that looks like during the time of Jurgensson. So, very interestingly, during the time of Jurgensson, how it looks like that he assumed the structure, the Jurgensson structure. What are the Jurgensson structure? Jurgensson structure. He told that cobalt is there, so ammonia, like, because on that time no chemical bond is discovered, so maybe that type of complex he assumed, and told that Cl, 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 and this is breakdown to put 3Cl minus ion. So this is the first structure, and the second structure is like that: CONH3, NH3, Cl, NH3, 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 Cl, and second one is the chlorine is there. And third structure according to Jurgensson, like NH3, 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 Cl, another 2Cl are like that way. Because here 3Cl minus ion, here 2Cl minus ion, here 1Cl. Because he told that the chloride which directly bonded to the metal cannot break down during the addition of AgNO3. So this is the probable structure. And third one, so this is the structure of, like, first one CONH3, means this is the structure of COCl3 dot 6NH3. After that, this is the structure of COCl3 dot 5NH3. This is the structure of COCl3 dot 4NH3. But what would be the structure of COCl3 dot 3NH3? He tried but cannot give any structure, no structure according to Jurgensson. Because if we put like that way, NH3, 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 then where we place the chlorine? So there is no position, because all chlorine should be there. But this is not possible. This ammonia cannot be free. That's why Jurgensson structure is, means, cannot give all the structure. That's why. So here the end of Jurgensson. And after that, Werner start his research. So before we go to the Werner's theory, we need to know some terms. Terms when you all know, just I remember one times again. What are double salts? Because before that, before Werner, no double salts or complex compound concept is there. Because what are double salts according to, on that time, people are looking for the double salts. So what is double salts? Double salts means two or more salts combined together to form a new salt. So this is called double salts. Two or more salts so suppose K2SO4 dot Al2SO4 whole 3 dot 24H2, that we know it is called potash alum, right? So it is very common alum. So if we dissolve this potash alum in aqueous solution like water, we will see 2K plus 2Al3 plus 4SO4 minus ions. Means total, so it will get 2 to 4 for 8 ions, and 3 types of different ions we will obtain. But so these are called double salts, means potassium sulfate, aluminum sulfate reacts in aqueous solution to produce a new compound. Similarly, if you go to the more salts, well, all we know that about the more salts. So if we go to the more salts, then what we observe, that in the more salt there are two mixture of salts are there. Ammonium sulfate and ferrous sulfate. Okay, in the more salt. So if we go to the more salt, then we know that NH4 whole 2 SO4, FeSO4, and then 6H2O. And if we put the more salt in aqueous solution water, then we get 2NH4 plus Fe2 plus 2SO4 2 minus ions. So these are called all are called double salts because they combination of more than one salt. That's why it is called double salts. But now what is the coordination compound? The coordination compound also a mixture of two or more salts. Coordination compounds are also the mixture of two or more salts, and they combine together to form a new compound which cannot dissolve in water, or if we dissolve in water they cannot produce all the ions. Like if you add KCN plus FeCl3, we will get like K3 Fe FeCN whole 6. Okay, so if we put this salt in water, then we get only 3K plus FeCN whole 6 3 minus, but we never get like Fe3 plus or 6Cn minus. We never get this. So these are called coordination compound. Similarly, you can write COCl3 dot 6 ammonia, which is the famous for Jurgensson. We obtained CONH3 whole 6 Cl3. Then if we put it in aqueous solution, we never get like CO3 plus or 6 ammonia. We never obtain. So these are called coordination compounds. And these ions, like if we get from this, we get CONH3 whole 6 T plus. This ion is called coordination ion or coordination compound. So each coordination compound have some coordination number, means each and every metal atom or metal ion contain a fixed number of ligands. You see here 6 or sometimes 4 or 5. So these are called ligands. So now what are the ligands? Because in the previous class when I discussed about the molecular orbital theory, here we discussed about cyanide, NO plus and CO. So there we have discussed that these three are pi acid ligands. So we use the term ligands. So what are ligands? Ligands are the species which ions or neutral molecule which can donate its non-bonding electron pair to the back end orbital of metal to form a metal ligand coordinate bond. It's called ligands. And there are, you know, that ligands are different types like monodentate, bidentate, tridentate, tetradentate, pentadentate, lot. That's all. So here we only focus ambidentate ligand. There are so only we focus on ambidentate ligands. Means ligands have more than one donor center, but this donor center simultaneously not used. Suppose cyanide minus, C111N minus. So it can form with all our organic chemistry. We know that sometimes it form MCN and sometimes we know that MNC. SN1, SN2, whatever it may be, that different story. So this is called ambidentate ligand because these ligands have two donor center, but every time a donor center used. Simultaneously not both donor center used. Similarly, SCN minus, similarly NO2 minus, nitrito, nitrate, O nitrito, that's are the ambidentate ligand. And after that, we have some deep insight into the ligands that is called accidental ligand. Okay. So what are the accidental ligand? Accidental ligand. So accident means we always try to tell that when we are into friends or three friends, hey, you are very flexible. Flexible means ঠিক আছে এখন এটা করব না পরে করব, মানে ডিসিশন নিতে পারে না, কখনো এই করছে কখনো ওই করছে, তখন আমরা তাকে বলি কি ফ্লেক্সিবল। তো এখানেও গল্পটা সেম। There are some ligands which can behave different donor sites in different times, like SO4 2 minus. It had two donor center, you see. So it can use as A minus O minus. So when metal come, that coordination is take place. And after some time, when another metal comes, then SO4 behave as a monodentate ligand, like this, and this is become OH. So this cannot donate. So it is. So here it is, you see, bidentate for two donor center. They are monodentate. So now here is very interesting one example is EDTA. EDTA is such a ligand which can act as a pentadentate and hexadentate. When it is EDTA T minus, it is pentadentate. But when it is EDTA 4 minus, it is hexadentate. Okay. So now, what is the structure of EDTA? EDTA means ethylene diamino triacetate and tetraacetate. This is the difference. So ethylene means CH2CH2, that is ethylene. Diamino means NN, diamine. Tetraacetate means C double O minus, acetic acid, yes, C double O minus, C double O minus, and C double O minus. Tetraacetate, you see 6 donor, 1, 2, 3, 4, 5, 6. So 6 donor center. When one group is replaced by one hydrogen group, then it is used as pentadentate. So now how the looks that ethylene diamine EDTA complex? We know that EDTA is commonly used for analytical purpose for the determination of hardness of water. We know that hardness of water determination EDTA is a very good ligand, means chelating ligand. So now what is chelate ligand? Chelate ligand is such ligands which can form a cyclic compound with the metal after coordination are called chelate ligands. Okay. So we know about the chelate ligands. So now what are the complex? Suppose if we put copper 2 plus EDTA 4 minus, then what would be the, we know that this complex is very much stable. Copper EDTA is very stable complex with K cat value very high, 2 minus. So now what the complex looks like? So how these 6 ligand use at a time with the metal ion. So if we to put copper 2 plus and then make a coordination sites like this, we just try to draw a structure. Now ethylene An CH2 CH2 N, right? Now you see that each N contains CH2 C double O minus. So O CH2 C double O minus, CH2 C double O minus, CH2 C double O minus, CH2 C double O. So this is the complex. Now overall charge is 2 minus. So this is the, you see that 1, 2, 3, 4, 5, 6, all the donor centers are simultaneously used. So now we have it act as a hexadentate ligand. That is called denticity. That means number of atoms donated to the metal to form coordinate bond are called denticity of the metal. And accordingly we get hexadental ligand or chelate ligand or ambidental ligand. Monodentate, bidentate, tridentate, tetradentate, whatever you use. And after that, another term is hepticity. We see that we generally eta 5 CP, eta 6 benzene C6H6, eta 2 ethylene in gaseous salt. So what are the hepticity? Eta is called hepticity. What is hepticity? That number of pi electron. You can say number of pi electron donated by a ligand to the metal, or you can say number of carbon atom connected to the metal. In two ways, you can say that number of pi electron donated to the metal by a ligand is called hepticity, or sometimes you can say that because hepticity generally we use all of the organic ligands, but you can say that number of carbon atom directly connected to the metal are called hepticity of the ligand. So you know the eta 5 CP cyclobutadiene, eta 6 benzene, eta 2 ethylene diamine, or eta 4 like that. Sometimes eta 2 C2H2 and eta 4 C2H4. Okay, so that's different story. So these are the denticity. So now, why I go from the Jurgensson to that area? Because Werner is the first chemist, inorganic chemist who tried to work on coordination chemistry directly, but Jurgensson is not an inorganic chemist, or Jurgensson is not work on coordination chemistry, because Jurgensson is a physical chemist. He just tried to discover the conductivity of the complexes, and based on the conductance, he put some idea that that should be the probable structure. But Werner first come and started his work with the Jurgensson complexes. And with Jurgensson done that complex, all the complexes was experimentally work done by the Werners. Okay. So according to Werners, what he did, just I briefly discussed Werners theory. Werner's theory. Actually, what he did after that, he put his theory. He has taken the complexes, all the compounds, okay, taken compounds, and moles of AgCl precipitated out, try to find out, and third, he measured the molar conductivity, okay, and after that, he tried to find out the number of ions within the complex. So these are the table if we look into it. So his first complex was COCl3 dot 6NH3, which Jurgensen gives some structure. He saw that 3 mole AgCl is precipitated out, and molar conductivity is almost like 430 ohm inverse, okay, ohm inverse, and number of ions equals to 4, right? Secondly, he tried to study second complex COCl3 dot 5NH3, and he found that 2 AgCl are precipitated out, and molar conductivity is just 250, and number of ions are 3. Third, what he have done, COCl3 dot 4NH3, moles of AgCl precipitated 1, molar conductivity 100, number of ions is 2. And fourth, he found that COCl3 dot 3NH3, number of AgCl 0, conductivity 0, number of ions 0. That means it is actually non-electrolyte. Non-electrolyte. And he put the name of this complex. This is called luteo-cobaltic chloride. It is called purpureo-cobaltic chloride. It is called prasio-cobaltic chloride. And this is no name on the time. This is just blue-green. So luteo, purpureo, and prasio-cobaltic chloride according to color, because luteo means orange-yellow, purpureo means violet color, and prasio means green color, or sometimes it is called violet again, and this is blue-green color. So based on this his observation, he put forward some theories. So what are the theories or postulates? We all know the postulates, so I am not writing all the things. Mainly he told that each and every metal ion contain two types of valencies. One is primary valency or ionizable valency, and another one is secondary valency or non-ionizable valency. And primary valency satisfy the oxidation state of the metal ion, whereas secondary valency satisfy the condensation number of the metal ion. So these two are the basic theory for Werner's. And third one is that each and every metal have fixed coordination number. When with octahedral, coordination number 6. When it is tetrahedral or square planar, coordination number is 4. So this is his theory. So based on his theory, he gave some structure of the complexes. What would be the structure? So first structure of the first complex like CONH3 whole 6 Cl3, and he told that structure should be like that way. NH3, 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 and 3 chlorine like that way. So these are primary valency, which is like 3, and these are the secondary valency, which is 6 here. So secondary valency is the coordination number, primary valency is the oxygen state. So that's why he represent the first structure. Okay. Similarly, he put forward the second structure. Similarly, and the third and fourth structure. So what would be the fourth structure? Just a minute. You want to join?